So welcome again for the last two presentations of this morning. The first one will be given by Antonio Criminisi. Antonio is leading the medical image analysis team at Microsoft Research Cambridge. And his current research interests are in the area of medical image analysis, in object category recognition, in image and video analysis and editing, and one-to-one teleconferencing, 3D reconstruction from single and multiple images with applications to virtual reality, forensic science, and history of art. Antonio obtained his PhD degree in computer vision at the University of Oxford. His thesis won the British Computer Society Distinguished Dissertation Award and was published by Springer Verlag. Antonio has won also a number of base paper prizes in top computer vision conferences.
Thank you very much for being here, for the opportunity given to me to speak to you about forests and jungles. It's all very equal, but you will see what I mean exactly by forests and jungles in a minute. So in this talk, I will be talking a little bit less about medical images per se, a little bit more about data and algorithms. But then I will be showing to you how these algorithms can be applied to medical image analysis applications. And we'll see at the end how everything comes together. So as a quick overview of my talk, I'll give you a very brief introduction to machine learning. There is a lot of talk going on about machine learning, big data, all these big buzzwords. But let's talk a little bit about what that actually means and what it is and what it can do for us. In particular, I will be focusing on decision forests and decision jungles as two specialized algorithms in the area of medical imaging. And then I'll talk about medical image analysis applications. We've done a lot of work in many different areas of medical imaging. I will not have time to talk about all of these tasks and applications, but the slides will be available to you, so all the information is in there and pointers if you're interested in this. So what is machine learning? I will be talking about one spatial part of machine learning, in particular about supervised machine learning. Even more specific than that, I will be talking about classification and later on also about regression. Imagine that we have some data, a lot of data. This data can be images, it can be reports of any type, can be textual data, can be web pages, can be anything that you can think of. And I represent that data with a little squares. So that's a single unit of data. That data normally, often, comes with some labels, which are represented there by the color dots. So you have red, blue, and green. These different colors can represent anything. Can represent, for instance, Alzheimer's patients versus Parkinson patients versus healthy individuals, or it can represent completely different entities like company number 1, company number 2, company number 3. And quite often what we want to do is we want to learn the correlation between the data, the measurements, which in our language we also refer to as features quite often, and the associated class labels. And so we do that by pushing all this data into our computers or in the cloud, and you run some algorithms which are called training algorithms for hours or days or weeks sometimes. And what those algorithms spit out is a model. In this case, we're talking about a classifier model, a classifier. And so what is this for? Why are we doing this? Because we want to be able to do prediction. So that in the online phase, in what is called the testing phase, if we're given just the measurements, no label associated with the measurements, but just the features, the box in this case, we push this into our classifier, and that spits out the correlated best, highest likelihood output label. So in this case, in the case of a medical imaging setting, you may say that the features that I put it as input into my classifier is some MRI image, for instance, and just by pushing this into my classifier, I want to be able to predict whether that represents an Alzheimer patient or not. Of course, this is a very simplistic view of machine learning, but I thought I would give you a brief overview so that at least we are all on the same page. So this is nothing to do with medical imaging. It's a toy example. Imagine that we have a large database of images, for instance, images from the web, and I want to be able to figure out whether these images belong to sharks or what is the other one, lizards. Now, of course, with your eyes and human brain, you will be able to say immediately, oh, this is an easy task. If it is blue, it's sharks. If it is not blue, then it's something else, right? So easy, of course. In this case, it is very easy. In real life, nothing is so easy. But indeed, if we, in this toy example, we represent each image as a set of very simplistic features, which are just two-dimensional, just two measurements. One of them is, say, the proportion of red pixels in the image, and the other one is the proportion of blue pixels, in the image. So if we use just those two measurements, we see that those images in the bottom row indeed corresponds to squares which are positioned very nicely in this two-dimensional Cartesian coordinate system, and there is a very clear separation between the two. Of course, we can use a higher dimensional representation. We can also use red, green, and blue. But we can use all sorts of other features. We can use gradients, we can use edges, we can use wavelet transforms, we can use a very high dimensional representation for each of those images. In fact, at the limit, we can use every individual pixel and measure everything from these individual pixels, and then we will have a million dimensional representation. So then the problem becomes, what is the right representation for the images? But a more important problem is also, how do I learn a generic function, a generic mapping, which, given any image, can tell me whether it belongs to, say, the left side or the right side? And this process is called induction. This is one of the keywords of machine learning. In this case, I want to find that sort of high-dimensional surface in this high-dimensional space, which separates in an optimal way the two sets of training images. Of course, again, this is a toy example, so the separation is very simple and very clear. But you can imagine there that rather than having the curve that I drew, I can have a straight line, or could have any other, an infinite number of other curves and hypersurfaces. So what is the correct one to choose? So these are the sort of problems, issues that machine learning deals with. Right. In practice, machine learning has given us things like gaming. I hope many of you have got an Xbox at home. The ones of you who don't, please go and buy one. And when you do that, remember to buy also the Kinect sensor. So Kinect, as many of you know, is a depth camera that looks at you, and what it does, it produces internally images like the one on the left, where each pixel there, rather than being colored like normally you would get with a snap, a portable camera, it gives you a gray value, and the gray value represents in millimeters the distance of the person from the camera itself. So for each pixel, depending whether it is dark in this case means, closer to the camera, and brighter means farther away from the camera. And this is a great sensing device, of course, but that's not the end of the story. Once we have that image, in order to enable the player to play games just by moving their body, what we need to do is we need to turn that image into a semantic set of measurements, some semantic information. And the way we do that is using machine learning by classifying, so it's a classifier type of machine learning, by classifying each individual pixel on the left with 1 out of 31 body parts. So we have manually chosen to divide the human body into 31 body parts. So left hand, right hand, forearm, head is divided into 4 squares, and so on. And so we trained on 1 million, roughly 1 million training images. We trained a machine learning classifier represented by the little cloud with nodes and edges. to be able to recognize for each individual pixel what part of the body belongs to. Of course, the image on the right is very noisy. It's not perfect, but we don't expect it to be perfect. But what's interesting is that it is good enough to enable you to play games. So no matter whether you're a woman or a man, whether you're wearing bulky clothes or gray, long hair or big mustache or glasses, whatever, it doesn't matter. The system has to work all the time. So that's what we did with classification type of machine learning. So let's talk a little bit more about the algorithm underlying there. And again, we're talking about gaming here, but you will see in a minute how there is no difference. What we've learned in the world of gaming has translated very quickly, very easily into the world of medical image analysis, which is fantastic to see. So one of the algorithms that we use there for doing this visual recognition of pixels and classification of pixels is called decision forests. So we build upon a very old, very well-known technique, which is decision trees. So when you study computer science, you study decision trees as a data structure. They're made of nodes. In particular, there is one principal node is called the root, and then there are internal nodes called split nodes, and then there are the leaves, the terminal nodes, which I draw like little squares. Now, this data structure can be used for doing very effective decisions. Imagine you see that picture of my kids on some random volcano in Europe, and you say, okay, I want to design an algorithm which can tell me whether that picture is taken outdoors or indoors. And so if I was to write a computer program, say in C or in Pascal or in Lisp, whatever your favorite language is, I would start by setting down some rules, right? And say, oh, look, I can check whether the top part of the picture is blue. If it is blue, then that's quite likely to be sky, therefore it's quite likely to be an outdoor picture. And guess what? That doesn't work, because I might be taking a picture of a blue wall. I say, wait a minute, if I'm taking a picture of a blue wall, then I can check if the bottom part of the picture is also blue. And then I go into a different if-then statement. Guess what? Rather than writing all these if-then, if-then, if-then statements by hand, I can learn them. I can learn them automatically through computation. That's all there is about machine learning, right? So rather than writing a program by hand, you learn that program in an implicit way by throwing a lot of data at the algorithm and learning to choose the right questions at the different nodes automatically, and therefore bifurcating left to right, through these many if-then statements automatically. That's a very simplistic view of machine learning. My boss will kill me, but don't say it out loud. So how do you, watch out. How do you actually go about deciding what the best questions to ask are, at which node of the tree and so on and so forth? So here's an example. Imagine that I've got this two-dimensional feature representation of 4 different classes of objects, color-coded with 4 different colors. What I can do is I can randomly choose how to split this space. I can start by having this linear split, and look at the distribution of the colors on one side of the line and the other side of the line, and say, does this separation produce pure or as pure as possible classes? Like, do I have all one type of color on one side and one type of color on the other side? And then I can choose a different line and do the same analysis. And this analysis can be done in a mathematical, rigorous fashion using some measure of goodness, if you want, which is normally called information gain. And there are many measures that can be used. Some of them are better than others. I keep repeating this until I say, oh, look, where is it? This is the best separation, because it separates those 4 colors into 2 clear and ambiguous colors on the left and another 2 on the right. And then, and I stick that choice, that's my question, which I ask to the data, I stick it into the root node of the tree. And then I proceed and I say, oh, now I look at the left child, that's what it's called, the left child of the root. And I say, oh, look, I found another good split here. And then I look at the right, and I choose this line. And it might not be a perfect separation, because there is still some green points, happening to be on the wrong side of that line. But it doesn't matter. We'll see that it doesn't matter too much. So in terms of the error measure or the measure of good fit that I use, like I said, we use information gain, which is again very old news. We didn't invent this. This has been around since Shannon's time, and it uses indeed Shannon's entropy to measure the purity of the class distributions. But also what we did, which some people have done, but not in a very systematic and rigorous fashion, is looking at how can we change this decision tree model and what happens when you change different bits and pieces of that model. For instance, the toy example I just ran uses this linear splits, but we can use something which is a lot simpler than that, and it's what we call axis-aligned splits, which turn out to be almost as good as linear splits, but much, much more efficient. So if you care about computational efficiency, which is very important when you have 4D, 5D, 10D sort of images, then you should use. Or on the flip side, if you don't care too much about computational timing, you care more about the accuracy of the results, you can use different sort of splits which have got more parameters, more degrees of freedom. For instance, you can use a conic section, you can use B-splines, you can use all sorts of models of hypersurfaces. And it turns out that each of these choices have got a huge effect on the final accuracy and also on what is called the generalization behavior of your classifier. Generalization is a very simple concept. It means that not only your classifier can classify the training data very well, but it also works well when previously unseen data comes into play. So it's a very important concept, and it's the opposite of overfitting. Overfitting means that you learn too much about the training data, so much so that when a new piece of information, new input comes in, it doesn't work so well. So this is a real decision tree that has been trained on images for doing these sort of classification tasks. So you see it's got a number of levels. In this case, we've got roughly 10 or so levels. It doesn't need to be perfectly balanced, but some branches can grow further than some other branches, and there are some different stopping criteria to decide how to control this. And given a test input, you branch left and right until you go to the end, to the leaf, and at the leaf there will be your response. This is an Alzheimer's patient or this is not. What's interesting is that it turns out that if rather than using a single decision tree, you use a set of many decision trees which have been learned with some randomness in them so that they're all slightly different from one another, you gain a lot in terms of generalization, this keyword that I was using 5 seconds ago. And so that's why nowadays we are talking a lot about decision forests rather than decision trees. It's just a silly name, but just to mean it's that we are dealing with an ensemble, a set of trees. And so now that we have many different trees, in probabilistic terms, we can say, given the same input image, for each of the trees, I reach a different leaf. At each of those leaves, I've got stored the probability of, say, that image belonging to the patient set or the healthy individual set. And all these probabilities for each of the trees will look slightly different. So how do we reconcile them? What do we do with all of them? Well, lots of people have thought of many different tricks, but the one that works best is the simplest. It's just averaging together all these different probability functions, sorry. There are many ways in which you can do the averaging. You can do geometric averaging, you can do algebraic averaging, and there are different behaviors. But all of this to say that we've done a lot of work in trying to figure out how certain engineering decisions and choices that you make into how to build these forests affect the actual results. And in this picture, we try to visualize this 4 spiral arm toy example where we have 4 classes, color-coded once again. And it's exactly the same training data in all cases, but you see that the shape of the colors changes wildly depending on what parameters you choose in when you train the forests. So please, if you try to apply forest or decision trees to your medical imaging problems, don't just download some piece of code, even mine is available, test it out and say it doesn't work. You have to understand what it does. The same goes with SVM or GMMs or whatever. You have to go a little bit deeper, understand what it does, understand what the parameters mean, and try to make it work for your problem. And it might not work, right? I'll show you some examples where forests work less well than other things, and that's fine. But I want you to give it a try. And there is code available, as an accompaniment to our book, which of course you have to go and buy as a prerequisite for passing the course. But having said that, the book itself is already obsolete, so maybe don't bother. Because there is a new set of techniques which are called jungles. So we go from decision forests to decision jungles. And why do we need that? Well, okay. So forests are great. They work very well in a lot of cases. But what happens is that when you train a forest, if you don't have enough training data, that training data gets diluted in an exponential way every time you branch out. So in average, every time you create 2 children from one parent node, you halve the amount of data you have for training each individual child. And you halve and halve and halve, so very quickly you run out of training data. And that means that the statistics of the training data at each node becomes diluted, becomes noisy, becomes less good for actually doing good training. And so that's not good unless you have a lot of training data, like in the case of Kinect, where we did have effectively an infinite amount of training data because it was all synthetically generated. So how do we fix this problem? We fix this problem by moving away from trees and using DAGs. So DAGs is directed acyclical graphs, also a very well-known data structure, which is not miles away from trees. But the key idea with DAGs is that some of the nodes will have 2 parents or more than 2 parents rather than a single parent. So still is a binary structure in the sense that each node has got 2 children, but each node can have, apart from the root node, each node can have 1 or more parents. So what happens, let me move over here. In this case, what happens is that, oh yeah, there we go. There's a laser pointer technology. Yeah, there we go, thank you. What happens is that for this node, data coming both from this parent and from this parent gets merged together. So if you do this merging of nodes in a clever way, you avoid or you can reduce a lot this problem of reducing and diluting the amount of data, training data that you have. Of course, now we have decision jungles as ensembles of entangled trees, if you want. So we didn't, that's our imagination. Not very good. So we can train many DAGs in a randomized fashion, just like we did with trees. And now we have sets of DAGs rather than sets of trees. And it turns out that this, in certain situations, can work a lot better than decision forests. So what's interesting is that, let me see. Yes, I'll go through this example, just to give you a bit more intuition about why this works and what it does for you. Imagine that we have a computer vision example. So I've got images of these sort of bucolic scenes, right? I've got cows and sheep and prairies and this sort of stuff. And I want to extract patches out of these images and automatically recognize whether each patch belongs to class 1, cow, or class 2, grass, or class 3, sheep. Again, it's a toy example, so bear with me. So imagine that I've got a very simple 2-dimensional feature space. I've got brightness and I've got chromaticity, and then this is where these 4 training patches distribute themselves. I can have many more training patches, and then I say, okay, I'm going to train a tree on this. So I start by having axis-aligned splits. I split once, then I split again, then I split again. So what happens is that triangles mean sheep and squares mean cow. So what happens is, because in this region I don't have enough training data, the system overfits, and it thinks that this whole region should be cow and this whole region should be sheep. But clearly, if you look at the faint ellipse, the generative model underneath, it should be labeled as sheep. So if instead we use DAGs, we start off in exactly the same way as trees. We split this way, then we split horizontally. Then we look at this child node and this other child node. We look at the statistics and say, oh, look, they are very similar with one another. It's just 1 point difference. So I'm going to merge them together into the same child, into the same node. And if I do this, then you get the correct generalization. And although I didn't have any training point in this region of the space, of the feature space, it manages to label it correctly at testing time. So what happens is that when we started working on DAGs to replace trees, we did it because we had some memory issues. The tree was way too big. It was growing in an exponential fashion. So we had to figure out a way of making the model fit on smaller amount of memory because we were developing applications for mobile phone devices. That's what we were doing. Again, nothing to do with medical imaging. And then we discovered that, oh wait, when we do this merging approach, not only we produce much smaller classifiers, but actually they work better too. And then we struggled to figure out why that was, and then we came up with some explanations, and this is not the only one. So I'm going to skip the part about how the actual training is done, because otherwise you will be bored to death. And then I will move on to talking about medical applications. How can all of this help in medical applications? So we have many areas, many tasks that we have looked into: anatomy localization, segmentation in 3D images, and many others as well. And so let's start with one. So the problem here is very simple. We have CT scans. This is just a coronal view of a CT scan of many patients. We have different resolutions, patients coming from all over the world, contrast, no contrast. And what we want to do is we want to automatically figure out where all the major anatomical structures are. And we parameterize the problem in a simple way by just saying all I care about is a bounding box in 3D which encapsulates the major organs. It could be the kidneys, it could be the pelvic bones, it could be the spine, or it could be the lungs, the liver, the spleen, and so on. And this is something that can help radiologists a great deal in their normal workflow. We do this by machine learning. We have a very large data set of 3D CT images, and with a lot of variability. All of these are patients, so none of these are health images, and they're all patients in many different ways. There is things like cysts, missing leg, there is, I don't know what that is. There are differences in resolution, in the presence or absence of contrast agent. You can have enlarged spleens or particularly small kidneys, kidney stones, or all sorts of issues. Tumors, of course. Having all this data, we hired someone to very quickly draw these 3D bounding boxes around organs, which is expensive, but not too expensive because it's just bounding boxes. And once we have all of this, what we did is we thought of the algorithm for predicting the boxes. So the parameterization of the problem is quite simple. What we want to do is this is a 2D example, of course, we want to predict the position of these bounding box walls, the left one, the right one, the top one, the bottom one, and the other two in 3D. And we do this by allowing every voxel V in the CT scan to vote probabilistically for the position of these walls. And now you might say, what sense does it make? I mean, if I have voxels which belong to air region, like outside the body, they all look exactly the same because they're all black, there is no density in there. They will all vote for a completely different position of the organs, and so you're going to get garbage out of it, and that's absolutely right. However, there will also be some points, for instance, near the vertebrae or other bony structures, perhaps the bottom of the spleen here, the bottom of the liver, which are very distinct in terms of their appearance, and they are very well localized. They can be localized automatically, and they can vote for the position of these bounding boxes with high confidence. If you look at the probabilistic distribution, it looks very peaked. And so what we do is through some maths and some algorithms that are based on trees, in this case on what is called regression trees, a variant of classification trees, we set out to automatically figure out of all the points we have in our 3D space, which landmarks are the ones which can vote in the most confident fashion, which ones can predict, say that in X here we have the position of one of these walls, which ones can produce probability distributions, density distributions in this case, which are as peaked as possible, as narrow as possible around the mean prediction. So that's a measure of confidence, and we use that for training our decision trees. And again, this can be trees, it can be DAGs, it works in exactly the same way. The algorithms and the implementation is not very different at all. So in terms of features, I said, we want to be able to figure out which pixels or voxels are discriminative enough, but also they are distinctive enough in terms of their appearance. And what we do is we look not only at values, the features which are embedded within the voxel itself, like its intensity, but also we look at the context around those voxels. So, if we are in this point here, the top of the right pelvic bone, then we look at big regions around here, or in here, and in here, and these are automatically chosen. These regions are completely automatically chosen by the algorithm. And so, if, given this rectangle here to the right side of the patient, we measure very, very low density, and in this other one we measure very high density, and in this other one we measure very average density, then it's quite likely that this point belongs to the pelvic bone. So all these if statements are embedded completely automatically within our tree architecture. So rather than, like I said, me sitting down and writing all these rules by hand, they're all discovered automatically by optimizing a well-defined cost function. So what we end up is something like this. We end up with a set of trees, and given a previously unseen CT scan, in this case it's an almost full body CT scan, we can push each individual voxel through all of the trees, follow them through until they reach a leaf, and for each of them, we get different probabilistic votes for where the position of 10 or 20 or 50 maybe anatomical structures are. And what we just saw in this spinning video is that not only we can figure out with great accuracy, millimeter accuracy, where the bounding boxes of these organs are, but we can also do automatic landmark detection. The landmark detection and localization is another of the key pieces of work done in medical image analysis normally. So these green regions that you see appearing and disappearing denote those clusters of voxels arriving at one of the leaf nodes, which produce very peaked, very high confidence in the prediction of the position of, the left kidney in this case, and the right kidney in this case that we're looking at right now. So interestingly, the system has automatically and by itself chosen to use, say, the bottom of the lung and the top of the pelvic bone, and decided that these are very good landmarks to use if my goal is to predict, the position of the kidney. So this part is unsupervised. I didn't tell the system what landmarks to use. All I said is, this is my task. I want you to do the best job you can at figuring out where the anatomy is. So a new, very recent piece of work that we did, following the same sort of structure of using regression forests, therefore predicting continuous variables rather than discrete variables, is something that I did with Daniel Alexander from UCL and many other collaborators. This will appear in MICHI 2014, so keep it to yourself for now. And so it's a very simple idea. If we, and Daniel pointed out some of these issues earlier, so when we do magnetic resonance imaging, right now the machineries are fantastic but very slow. You don't want to keep the patient in there for way too long. especially when you do diffusion tensor imaging, which is looking at the way in which the water molecules diffuse inside, say, your brain or the heart or other structures of the human body. That can be a very time-consuming process. And of course, it is extremely time-consuming if you need very high resolution. So the idea is, what if we acquire those images, say this is a diffusion MRI type of image, in very low resolution, and then we use machine learning techniques to translate this into a higher resolution image. And guess what? In this sort of problem, we can have as much training data as you want, or almost, because what you can do is acquire a lot of very high resolution images, downsample them with whatever your favorite technique is, and now you have pairs of low resolution, high resolution images, which you can use as training images. And that's precisely what we did. And so, the model in this case is extremely simple. Given all the blue dots which represent the position of voxels in a low resolution image, we want to predict the red box, the red dots, which is the high resolution voxels. We can do this using decision trees. We can do this using bilinear, bicubic, or whatever other interpolation techniques you want. And interestingly, we can use this not only for diffusion MRI, but we can use it for NODI parameters. We can use it for the brain images that Daniel was talking about earlier. We can use it for motion analysis as well, sequences. Of course, we haven't done all of this. We've done just these two types of images, and the results are very, very encouraging. So we show very clearly that when we use forests, ensembles of decision trees, we manage to get much lower reconstruction errors than when we use other techniques, more standard sort of techniques. Finally, this is another very recent project, which will also appear at MICAI 2014. And I think we should institute a prize for the longest title or the longest author list, because we definitely win that. But the long title is really a byproduct of the fact that we're working with tons of doctors and tons of people who really care about this. So this project is about multiple sclerosis, and there's been many, many papers written in the MICAI community about multiple sclerosis, but most of them, what they do is they look at patients' brain images, brain MR images, and you look at the plaques and you try to count them or try to segment them, do this sort of stuff, which is fantastic work, of course. I've done some of that myself. But it turns out that when I started to talk to those neurologists, they said, oh, that's not very useful. Because you might have a patient with a lot of plaques, but their daily life is not impacted much. Because the brain has got this fantastic power of remodeling itself and bypasses some of the problems and readapting to making sure that you can keep leading a good life until a new event happens, a relapse, and then you degenerate a little bit and then remodels itself again. So what's more important is instead to measure how well you do in your daily life activity. And as a surrogate for that, what we did is we came up with an idea where we can stick a Kinect in the patient's bedroom or living room, and they can be perhaps playing their favorite game, using their body, and while they have fun and do some physical exercise, you can actually measure how well they do, not just in terms of the gaming score, but in terms of their gestures. What are they doing? How fast are they shaking or not? Can they keep their balance or not? So by working with all these people, we've devised a set of movements. There is 9 movements. These are just some of them, like the standard neurological test where you touch your nose with eyes open or eyes closed, or you can try to touch your fingers like this, or you balance on one foot. You stand still like this to see whether you wobble about or not. And all these things can be measured through our pipeline, which involves the usual sort of pre-processing steps, and then given a depth video captured with a Kinect sensor and some features very similar to what I showed to you in the CT scans, we can apply our classification forest technique, in this case not regression, and come up with very good numbers. These are DIE scores, I believe, which show that in the case of truncal ataxia, forests are the best algorithms to use. I'm about done. for classifying patients versus healthy individuals. In other cases, for other movements, it looks like either linear or non-linear support vector machines work better. And we don't quite entirely understand why these differences. We have 9 movements to look at in total. We haven't had the time to do this. But also the problem that we're facing next is how do I go from this movement by movement categorization to actually giving a rating, a score for the individual, which can be really good for tracking the disease progression. Again, just like we did in CT, not only we want something that works, but we want to understand why it works. And this is what's cool about this sort of machine learning techniques. They're not just black boxes, but you can look inside the trees and figure out what are the discriminative landmarks that fire up in each situation. And so this is a heat map that tries to show the differences between truncal ataxia and touching your nose. Clearly, this movement is very important. So when you get to your finger close to your nose, that's where most of the attention is paid to by the algorithm. So I leave you with this sentence, which I really completely believe in. I think that modern and efficient machine learning has got that potential to revolutionize medicine. So thank you very much.